All right, everybody, welcome here. Another quick video on a couple of important topics: molar mass and our friend Avogadro's number. Why not? So today we're going to talk about these two really conversion factors. Is really what they are, how we use them, do a couple of calculations involve them. So hopefully we get an understanding of them. So let's start really with Avogadro's number. Avogadro's number has to do with our friend the mole, not the furry guy, but the mole. It is abbreviated, by the way, MOL. They had to do some type of abbreviation, so they got rid of the E. So it's important, though, that a lot of times people will see MOL and they'll think molecules, but it is actually the abbreviation for mole. I would say probably if they want molecules, most of the time they'll write out the word molecules. If not, you see this MOL, it's going to be moles. So what is a mole? Well, a mole represents a certain amount of something. So for example, in our life, we know that when we say we have a pair of something, that equals 2. Got a dozen of something, that equals 12. And the same thing goes with a mole. When we have a mole of something, it actually does equal a number. It equals 1 mole of something will equal 6.022 times 10 to the 23. Now the unit associated with this does vary sometimes. I would say most of the time they could be units of atoms. They could also be units of molecules. Frankly, they could be anything. So you got like pizzas or something you got going on there. Sounds good right about now. Shoes, whatever it may be. Although the occasional shoe might pop up in the chemistry calculation, probably atoms and molecules are going to be probably the two units that you most often will see. Particles as well are sometimes used, but atoms, molecules, probably most of the time. So what is Avogadro's number? Well, Avogadro's number really is that number we just saw. Avogadro's number is 6.022 times 10 to the 23. Now, Avogadro's number is really used as a conversion factor to go between basically these units, moles to atoms, or really it could also be molecules if you're dealing with molecules. Or if you're starting with atoms or molecules, to go back to moles. We use Avogadro's number as a conversion factor. So for example, if we had 1 mole of hydrogen, that would give us 6.022 times 10 to the 23 atoms of hydrogen. So that is an equality that means you could really write two conversion factors to use: 1 mole of hydrogen over 6.022 times 10 to the 23 atoms. Or like any conversion factor, you basically just flip it around and put the 6.022 times 10 to the 23 atoms up on top and a mole on the bottom. Now, we use both of these conversion factors. Like most conversion factors, no, you'll use whichever one that you need for your calculation. So for example, if I said I had 4.5 moles of hydrogen and I want to know how many atoms of hydrogen that is, we would do a conversion factor: 4.5 moles of hydrogen. And just like dimensional analysis here, remember, not really written as a fraction, but moles are up on top, opposites cancel. Conversion factor here on the right will do that for you: 6.022 times 10 to the 23 atoms of hydrogen is a mole of hydrogen. When we set up dimensional analysis like this, we are going to multiply on top and divide by what's on the bottom. We covered this in an earlier video. Maybe I'll put a link up here so you can find it. But basically, that's going to cancel out our moles. And we're going to basically grab our calculator wherever it went. There it is. And we're going to go 4.5 times 6.022. You do want to make sure you use your exponent button. Remember, on your calculator, it probably looks like that. looks like that when you're typing in scientific notation. So E23 gives us 2.7 times 10 to the 24 atoms of hydrogen. Now, let's say we had something that wasn't just something off the periodic table. Let's say we had a compound, say something like water. And water is a molecule. It's also a compound. And we can also use Avogadro's number with that. We could say if we had 1 mole of water, we would have 6.022 times 10 to the 23. And in this case, we'd actually use molecules here because water is a molecule versus hydrogen, which is just an atom of water. This also, much like the hydrogen example, will give us a couple of conversion factors there. 1 mole of water over 6.022 times 10 to the 23 molecules of water. Once again, we can flip this around, get our other conversion factor. Basically just put in our Avogadro's number here up on top over our 1 mole of water. So let's say in this case, we actually had 1.25 times 10 to the 16 molecules of water. And we want to know how many moles that is. So again, we would use Avogadro's number here as a conversion factor. We'll take our 1.25 times 10 to the 16 molecules of water. Once again, not really written as a fraction, but it helps you visualize it. Just put it over 1. That helps you when you do dimensional analysis because, again, opposites cancel. I could clearly see molecules up on top, which means that's going to be the winning conversion factor. Molecules on the bottom opposite location. 6.022 times 10 to the 23 molecules of water in 1 mole of water. Once again, multiplying always the top, dividing always the bottom. Molecules of water will cancel. We will be left with moles. So 1.25 to the 16 times 1 basically divided by 6.022 to the 23. Going to give us a lot of zeros. That's a lot of zeros to count. How about a little scientific notation there? So we'll go with 2.08 times 10 to the minus 8 moles of water in this case. Now, again, that's in scientific notation. On your calculator, it might have the decimal form. And a reminder that that's okay, except you might not want to write all those zeros. So that's a lot of zeros. I can't write my zeros straight. That's bad. So on my calculator, this is really what it looks like on my display. It kind of cuts it off here as it runs out of room and gives it to a 0. All right. So Avogadro's number is used whenever we are doing any type of conversion involving atoms or molecules. You could use Avogadro's numbers from anybody on the periodic table. So 1 mole of carbon would have 6.022 times 10 to the 23 atoms of carbon. 1 mole of fluorine would have 6.022 times 10 to the 23 atoms of fluorine. You could also, again, do it for any type of compound. 1 mole of methane would have 6.022 times 10 to the 23 molecules of methane. 1 mole of nitric acid would have 6.022 times 10 to the 23 molecules of nitric acid. Again, for all of these equalities, you could write 2 conversion factors to convert. Now, again, it is if you have moles, you are going to set it up dimensional analysis. You're going to basically multiply by Avogadro's number. Again, that could be atoms or molecules. Again, multiplying and dividing, and that will get you the moles to cancel and leave you with atoms. Again, you could also do this with molecules, as we've been talking about. If you're starting with atoms, or even, again, molecules, you can divide by Avogadro's number. So 6.022 times 10 to 23 atoms per mole, or again, could also be molecules down here. Atoms will cancel as we are multiplying and dividing. Going to give us moles here, what we're looking at. One common mistake that people make is this. They learn Avogadro's number. They like the 6.022 times 10 to the 23, and they want to use it in every calculation. You really should not. So in order to use Avogadro's number, you need a couple of keywords. One is you're either given a number that's in atoms or molecules or particles, or you're asked to solve for something in atoms or molecules or particles, pizzas, whatever it may be. If you don't hear anything in a problem, or they don't mention anything about atoms or molecules, you should leave Avogadro's number on the side. You probably don't need it. So common error, people want to use it in every calculation, should only be used really when you hear these keywords. One of those keywords, either they're given to you a number in those atoms or units, or you're looking to find something like atoms or molecules. Otherwise, don't use Avogadro's number. So that's Avogadro's number. Again, the conversion factor you probably use more than Avogadro's number is really molar mass. And molar mass has units of grams per mole. And we calculate the molar mass and we get a number. And that number is always how many grams there are. So the number you calculate always goes with the grams part. And it's always per 1 mole. So the mole should usually never have a number with it. It should always be 1, basically. And those are the units. It is frankly a conversion factor. And it is a conversion factor that allows you to go from grams to moles and moles back to grams. Those are the basically conversion factors that you can do. So where do we get this great conversion factor? Where we get a lot of things in chemistry, a little periodic table action, right? We go to the periodic table, we go to the boxes there, we pull up O, and on the bottom are some numbers there, 16, for example. We go to periodic table, we go to carbon, we see 12.01. Go to periodic table, you find hydrogen, 1.008. All of these numbers, which are on the bottom, which you might have learned is the atomic mass, is also considered the molar mass of each of these things. And when you go to periodic table, it is typical you go about 4 significant figures for that number on the bottom. It will vary depending on your periodic table. Some may have a lot more digits, some may have less digits, but the general rule is we're going to take a molar mass off the periodic table. That's 4 sig figs that you want to pull off there. So let's just take oxygen, for example. 1 mole of oxygen from the periodic table would give me 16.00 grams of oxygen. That is the molar mass of oxygen. We could use that as a conversion factor, 16 grams per 1 mole. And that is typically how you refer to molar mass, is 16 grams per mole. Frankly, it is still a conversion factor. So you could, if you needed to, flip it around and use it in this fashion and do a little dimensional analysis problem. So again, if I had 4.5 moles of oxygen. And I want to know how many grams that is. I'm going to set up a dimensional analysis. And again, not really written as a fraction, but if you want to help yourself, you can put it under or one underneath it. That means moles are on top. Again, to get rid of moles, we got to go opposite location. So 16 grams of oxygen per mole of oxygen. Moles of oxygen cancel. Once again, dimensional analysis, the beauty of it, multiply the top, divide the bottom. Don't have to worry about math too much. We go a little 4.5 times 16. That's going to get us 72 grams of oxygen in this case. We can calculate the molar mass of anybody. If we were going to pull it off for carbon, it would be 12.01 grams per mole. Again, you could flip that around and put the moles on top, the 12.01 grams on the bottom. For hydrogen, 1.008 grams per mole is the molar mass of hydrogen. Just like we saw with Avogadro's number, you absolutely can do molar mass for something that's a compound or a molecule. You basically just add up all the parts. So in this case, we would have to go to periodic table. Once again, find our hydrogen box, go to periodic table, find our oxygen box. And now we're ready to get the molar mass. So we're just going to add up the parts. So this 2 goes to the element to the left. Nothing written there means 1 goes to the element to the left. That means we have 2 hydrogens, each at 1.008 grams per mole. And that takes care of the molar mass of hydrogen. We have 1 oxygen from the periodic table, 16 grams per mole. And if we add that together, that's going to give us 18.02 grams per mole. Again, number stays with the grams. It is per 1 mole. That is our conversion factor that's going to allow us to go from grams to moles or moles to grams. We again could write that as like a conversion factor, 18.02 grams of water over a mole. Or we could flip it, a mole is 18.02 grams. So let's just say in this particular case, we had 42.5 grams of water, and we want to know how many moles that is. So again, we would start with 42.5 grams. We're going to divide in this case and get grams in the opposite location. So once again, grams are up on top, opposite cancels, 18.02 grams of water on the bottom per mole of water. Once again, dimensional analysis, multiply the top, divide the bottom, and here the grams will cancel. We'll take 42.5 divided by 18.02. Gonna get us a 2.36 moles of water. So you can absolutely add up all the parts for a formula and you'll get what you need in terms of the periodic table and the molar mass, which is a conversion factor. So again, our molar mass is our conversion factor to go from grams to moles and moles back to grams. So once we had some long formula like C2H5OH or something like that, basically we just add up the parts. It doesn't matter. So again, we go to periodic table, find carbon, go to periodic table, find hydrogen, go to periodic table, find our friend oxygen. And again, we're just going to add up all the parts here. So again, in this case, we have 2 carbons, each at 12.01 grams per mole. That's basically our carbons. We have actually 6 hydrogens, 5 there and 1 there is 6, each at 1.008 grams per mole. Again, for our hydrogens, and 1 oxygen plus our 16 grams per mole, which is for oxygen. And again, all we're going to do is just add all that up So 2 times 12.01 plus 6 times 1.208 plus a 16. Going to give us a molar mass for this guy, 46.07. Again, the number goes with the grams part, always per 1 mole in this case. And again, we could use it as the molar mass just like that. Or if we're doing dimensional analysis, we could flip it around and use it in the other direction as well. How do molar mass and Avogadro's number relate to each other? Well, if you have 1.008 grams of hydrogen, that equals 1 mole of hydrogen. And by the way, 1 mole of hydrogen equals 6.022 times 10 to the 23 atoms of hydrogen. You got 18.02 grams of water. That equals 1 mole of water. And that equals 6.022 times 10 to the 23 molecules of water. So what ties grams and molecules together and grams and atoms together? As you can see here, it is actually moles. Moles is the unit that basically ties those other units together. It's kind of the central stopping point between those two units. So why would we need to worry about that? Well, we take a pen that writes here, have something, there you go. Let's just say we wanted to know if I have 32.5 grams of hydrogen, how many atoms of hydrogen would that be? Well, I would take my same approach. This has atoms in it, which means somewhere along the way I got to use Avogadro's number. I'm in grams. So again, my pathway here is I know I could take grams to moles, and that's the molar mass from the periodic table. I know I could then go moles to atoms, and that's Avogadro's number. So that is the pathway. And again, you can see moles are right in the middle of it. So again, I would go to the periodic table, find my hydrogen, 1.008. That's my molar mass. We'll start my calculation, 32.5 grams of hydrogen. Again, we want to go opposite. So grams are up on top, which means 1.008 grams per mole of hydrogen. Again, that is from the periodic table. And that is this number right here. That number there is how many grams there are per mole. We stop the calculation right at this point. We're going to multiply the top, divide the bottom. Grams will cancel, and we're in units of moles of hydrogen. Now, again, we can see the units of moles are up on top, and we want to take it to atoms. So this is where Avogadro's number comes into play, which is basically this relationship. Moles are on top, which means 1 mole of hydrogen on the bottom, 6.022 times 10 to the 23 atoms up on top. Again, multiplying and dividing, and our moles will cancel, going to leave us atoms here. So essentially here, we're going to take 32.5 multiplied by 6.022 to the 23. We're going to divide it by 1.008. Going to get us here in the 32 grams or so of water, of hydrogen, 1.94 times 10 to the 25 atoms of hydrogen in this case. So again, a reminder, when you're punching in Avogadro's number here, 6.022, probably an exponent button, EXP button, and 23 would be, again, how you would punch that in. Probably on your display, you might see 6.022E23 or 6.022 times 10 to the 23. It may pop up a couple of zeros up there when you punch in your calculator. So really important when you're doing Avogadro's number, make sure you use that exponent button. Some of the newer calculators, by the way, have a button that looks like this for the exponent times 10 to the n. And usually those button calculators have a wheel on it. They're kind of two-tone usually. The side's a different color than the main calculator part. If you have that one, you would actually punch Avogadro's number in like this. You gotta go open a parentheses, 6.022. You gotta then hit your exponent button. And then the rest is kind of like normal. You'll hit your 23. Then you need to hit your wheel, this right here, this side of the wheel, and close your parentheses. And that should be how you punch it in if you got that type of calculator. You got one of these buttons here. You don't need parentheses. You could just punch it in like normal. So once again, molar mass is probably the conversion factor you'll use the most in chemistry. It is grams per mole. And one last thing about molar mass that people oftentimes will mess up on, let's just say we had an equation such as this. And let's say you're doing a calculation and you need the molar mass of NH3. Well, if you need the mass of NH3, you would go to the periodic table. You would find nitrogen, 1401. You find hydrogen, 1.008. The molar mass of NH3 would be 14.01 grams per mole. And that's for our nitrogen. Plus 3 times 1.008 grams per mole. And that's for our hydrogen. And that's going to give us here 1703 grams per mole that we could use as a conversion factor. Again, the number stays with the grams. It's always per 1 mole. Now, some of you may be asking, hey, what about a better color to highlight with? How about that one? What about the 2? Don't I need to do my molar mass and times it by 2? The answer is no, unless you want to get it wrong. So molar mass should always be calculated based on the formula alone. Regardless in an equation, the number or coefficient in front has no effect on the molar mass. If I was going to do H2, it would just be 2 times 1.008 for hydrogen. That's it, not the 3 involved as well. And this would just be 2 times my 1401 for our nitrogen. The reason for that is the actual definition of molar mass, grams per 1 mole. So it is per mole, which means whenever you're calculating the molar mass, regardless of what the coefficient might be in a balanced equation, you should only do it for the formula by itself. So you just take the formula out by itself and you calculate the molar mass from the periodic table, and that is how you do it. You never ever incorporate the coefficient when you're calculating the molar mass. All right, that should wrap up molar mass, Avogadro's number. Hopefully that was helpful for you. Thanks for watching. We'll see you on the next one. Bye-bye.